Hello and welcome to The Explainer. Today, we're diving into a power hidden so deep within the laws of nature that it almost feels like a secret. A power that, once we figure out how to harness it, could change absolutely everything we know about computation. So, shall I tell you a secret most computers wish they knew? That's really the question, isn't it? Because we're not just talking about building faster machines here. We're talking about a completely different way of, well, a different way of thinking. Okay, let's get right into this. I want you to imagine a cheat code, one that's written right into the very fabric of the universe. This isn't just any code. It allows a new kind of machine to whisper the answers to problems so mind-bogglingly huge that our best supercomputers today would take millennia to even make a dent. Now, this cheat code, it gives us two incredibly powerful keys. The first one is like a master key for the entire digital world. You know, something that could pop open almost any secure vault online. But the second key, that's more like an alchemist's key. It's the one that can unlock the fundamental chemistry of life itself. These aren't just clever tools, these are potential world changers. So let's start with that first key. We're about to see how it can crack the world's toughest digital fortresses, not by using brute force, but by turning an impossible math problem into, of all things, a beautiful piece of music. The lock we're trying to pick is something called RSA encryption. It's the bedrock of our modern internet security. We're talking every password, every online bank transaction. And its entire strength relies on a really simple idea. Multiplying two gigantic prime numbers together is easy. But taking that result and trying to figure out the original two primes, for a normal computer, that's practically impossible. And for decades, this math problem was an unbreakable fortress. Then, in 1994, a mathematician named Peter Shor came along. He didn't try to smash the door down. No, he found a hidden frequency, a way to make the lock resonate with itself and just click open. His discovery created this crystal clear before and after moment, and it kicked off the frantic global race to build a machine that could actually perform his magic trick. And the difference here is just staggering. I mean, what would take a classical computer longer than the age of the known universe to figure out? Shor's algorithm turns into this quick, elegant dance. A task that would take an eternity becomes, well, fleeting. So what is the secret? I mean, how does it actually work? Instead of just guessing factors one by one, the brute force way, the algorithm listens for a pattern. It finds a hidden rhythm, like a secret heartbeat inside the math of the problem. And once you find that beat, that period, the whole problem just unravels. So how is this music actually composed? You can think of it as a four-step process. First, you get your quantum canvas ready. Here, the qubits exist in superposition, which means they're holding all the possible answers at the exact same time. Then, you paint on this canvas, applying a function that lets all those possibilities mix and interact. But the real magic, that happens in step 3. You use something called the quantum Fourier transform. It acts like a musical crescendo, amplifying the one correct rhythm and making it super loud, while all the other noise just fades away. And finally, you just listen. You take one measurement and boom, the beat, the period is revealed. And that gives you the key to the entire solution. Okay, now for our second key. With this one, we're shifting gears. We're moving from music to alchemy, from cracking codes to, believe it or not, cooking up the future of medicine and materials. The problem we're tackling now is one of absolutely staggering complexity. You see, trying to accurately simulate a single complex molecule on a regular computer is, as the source so beautifully puts it, like trying to conduct Beethoven's Fifth Symphony using only spoons. It's just, you don't have the right tools. The complexity explodes because molecules are quantum systems, and classical computers simply don't speak that language. The solution is this incredibly clever algorithm called the Variational Quantum Eigensolver, or VQE for short. Now, it doesn't try to brute force the problem. Instead, it creates a partnership, a kind of hybrid system, where a quantum computer does all the heavy lifting and a classical computer acts as its wise guide. And their shared goal is to find a molecule's ground state, its most stable, lowest energy form. Think of it like a quantum kitchen. First, you create a flexible recipe. That's your quantum circuit.
Then, the quantum computer does its thing. It mixes all the possible ingredient variations at the same time, all thanks to superposition. Step 3, you taste it by taking a measurement to check the energy level. And finally, your classical computer, the head chef, analyzes that taste and suggests some tweaks to the recipe. You just keep repeating that loop until you find the perfect, most stable blend.
Now imagine doing this in a classic kitchen. You'd have to try one recipe, see it fail, make an adjustment, and repeat that process over and over for ages. It would take forever. But the quantum kitchen, it explores everything simultaneously. It finds the perfect recipe almost instantly. So we have these two incredible keys. One finds a musical beat to shatter codes, and the other tastes every possible recipe at once to design molecules. But what does this all actually mean for us, right here, right now? Let's take a look at their echoes in the real world. So let's just put it all together for a second. On one hand, you have Shor's algorithm, which listens for a hidden beat to crack a really hard math problem. On the other, you have VQE, which tastes every recipe at once to solve a chemistry problem. You've got two wildly different challenges, but both are solved by tapping into the same strange and powerful rules of the quantum world. And this is not some far-off sci-fi fantasy. The theoretical power of Shor's algorithm is the reason that, as we speak, cybersecurity experts are in a global race to build quantum-resistant encryption. And VQE, it's already running, right now, on our current imperfect quantum computers. It's simulating small molecules and taking the very first steps toward designing brand new drugs and revolutionary materials. We've seen how a new kind of rhythm, a quantum rhythm, can turn chaos into clarity, and in doing so, it can shift the very ground underneath our feet. This all brings us to one final, and I think, crucial question. We've seen how a single new idea, just a different way of looking at a problem, can completely rewrite the rules of computing, security, and science. It just goes to show you the biggest breakthroughs don't always come from more power, but from a whole new perspective. So that leaves us all with one final thought. What tune will you play next?